Hello, everyone, and thank you for joining me. Welcome to MEGGER's special webinar series. Today's topic is best practices for current transformer testing. My name is Michael Fleischer, and I'm the Digital Marketing Specialist from MEGGER. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Our presenters today are Abel Gonzalez, Applications Engineer, and Mike Ditmore, Applications Engineer. Also, to assist with the question and answer session, we will have two panelists joining us today. We have Dinesh Chajer, Technical Support Group Manager, and Daniel Carreño, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Abel.
Hi guys, thank you all for joining us on this webinar. We will be presenting about current transformers. The presentation will be divided in two parts. There will be a small theoretical presentation at the beginning, and then we will have hands-on at the end. I will present the first part, and my colleague Mike will present the hands-on where we will test a real CT with our tools. Now, on the agenda, we have current transformer definition and fundamentals. We have field tests for current transformers, and as I mentioned, we will be testing a CT with the MRCT. Now, what is a current transformer? Well, a current transformer is an instrument transformer with its primary winding connected in series, as you can see on this model here on the right, with the conductor carrying the current that we want to measure or control. Now, when you have current circulating through this conductor, a magnetic field is created, which in turn creates a voltage on the winding that we call the secondary winding, which will make a current circulate when we connect a load to that winding. What we see here is real implementation of the concept that we're showing on the right. This is what we call a bar current transformer. Now, what are current transformers used for? We use them to supply a reduced value of current, either 5 or 1 amps, to meters, protective relays, and other instrumentation. One of the reasons why we use current transformers is to protect the personnel and apparatus from high voltage, while allowing a reasonable amount of current in each of these applications. Now, the secondary of the transformer will supply a current that accurately reflects a proportional value of the primary current with the smallest phase shift possible. We will see that a little bit further on. We have, as applications, we have metering CTs, which are used to maintain a high degree of accuracy over the full range of current levels, from all the way from 10% to 100% of the full load. We will discuss higher accuracy applications at the end of the presentation. We use them to measure and to bill the energy usage, which relies on inputs provided by CT metered installations. Now, to protect against this revenue loss, many utilities implement in-service testing programs for their CT metered installations. We will talk in the presentation about the tests that you're supposed to perform on CTs to prevent that those losses that we were just talking. Now, we also have protection CTs. The protection CTs serve as inputs for a power system's fault protection. They must be accurate under overload and fault conditions, unlike metering CTs, which are supposed to be very accurate from very low currents until 100% of the CT's nameplate. Protection CTs need to be accurate beyond the normal current of the system, because it is when you have a fault in the system, high current conditions occur under which we need to be able to measure. That's why IEEE C57 specifies that protection class CTs need to maintain a plus minus 10% ratio accuracy over a range from 1 to 20 times the rated secondary current at the specified burden. We will talk more about it a little bit further on. Now, there are differences in performance and operation, and also in the concept and how you build a voltage transformer, shown here on the left. In a voltage transformer, you have two very well-defined windings that we call the primary and the secondary windings, where you have several turns on the primary and several turns on the secondary. In the case of the current transformer, the typical current transformer and the most common one, you only have one turn on the primary. You could have one type CTs where you have several turns on the primary, but the most typical one, you have only one wire or one turn going through the core. This will be your primary with only one turn and many turns on the secondary. Now, the construction types of current transformers, we have several that we're not mentioning here, but the most common ones are the window type, where you simply have a window, like the name of the transformer indicates, through which you have to pass the conductor that you want to measure the current on. You have a bar type transformer, where you would connect your primary on both sides of the bar, and you have a split core, which is a transformer where you can open the core, put it through across the winding, and then close it, and it makes the installation a lot easier. As you can see, they all correspond with the model that we have here on the right, and it's the reason why I like to show the model along with the picture of the transformers here. Now, the typical field tests that you do on a current transformer depend on what the current transformer is. Well, the current transformer, as we saw on a previous slide, is a device that has a winding, and the winding is made of copper, and therefore has some resistance that you have to measure, but it's also a device that has a separation between the primary and the secondary, and therefore, being an electrical device, the first test that you have to do is the insulation resistance test. Now, the insulation resistance test, we will talk about it later. It's the, I would say, the most basic of all electrical tests, and you have to do it on every device out there. Now, the second test depends on the fact that that winding will have a resistance, and you need to check that resistance to verify the proper operation of the instrument. Now, it is a magnetic device, and therefore will have a excitation or saturation curve, and you need to measure how the saturation or excitation curve of the device is performing. And being a transformer, you need to verify the transformer's ratio and the phase deviation, as well as the polarity of that transformer. Now, there will be load connected to that transformer, and therefore you need to measure the burden, which is the load that's connected to that transformer. Now, one of the things that you do on a transformer is you need to verify that the transformer is demagnetized when you finish all your testing. The CT demagnetization, even though it is not a test per se, it's more of a procedure. It is something that you need to perform not once, but sometimes several times during the testing, depending on the types of tests that you are performing on the CT. When you're testing, the first thing that you have to do, and I wanted to just give you a small reminder here that safety is first. You need to protect the personnel and equipment. You need to follow local safety policy and equipment operation instructions. You have to review grounding, lockout, and tagging practices in general. Everything that goes with safety comes first. That's why I wanted to mention it here. It's something that you cannot overlook under any circumstances. Now, the first test that we are going to discuss is the insulation resistance test. As you can see here, we have connected a DC test to the primary and the secondary. So in this case, what we are showing here is the measurement of the insulation resistance between the primary and the secondary. You can also, changing the connections, measure the insulation resistance between the primary and ground and the secondary and ground. Generally, the accepted minimum insulation resistance for one CT is 1 mega ohm. Now, every utility out there has their own, I would say, standards for how much is the minimum insulation resistance that you can, let's say, accept. But whatever it is, you have to compare your results with that minimum and take decisions with with that number in mind. One of the most common reasons for the low insulation resistance measurements is the presence of moisture. If you have low insulation resistance values, you have to solve that problem before you continue any other procedures, and you have to solve that problem before you put the device back under in operation. Now, when you're doing the test, the insulation resistance test on the CT, you're not only testing the insulation resistance on the CT, but you're testing the insulation resistance of all the wires that you have connected to the CT. Of course, it depends if you have the CT in your bench or if you have the CT in the field. But if you have it in the field, then wherever you are connecting, you're also testing the insulation resistance of that as a whole. So low values of insulation resistance could indicate a problem on the CT, but it could also indicate a problem in the cabling. Remember, you have to solve this problem before you proceed with the rest of your testing and before you put the CT back in service. The second test that we talked was that we mentioned was the winding resistance test. Now, the winding resistance test measures the CT winding resistance, or the DC winding resistance. Remember, it's different, the DC and AC winding resistance, because of the skin effect that presents when you have alternating current circulating on a conductor. Now, for this, we inject a test current into the winding. We measure the corresponding voltage drop, and the resistance will be the division of the voltage and the current that we injected. Now, a DC test will always cause a residual magnetization of the core, which may affect other test results. You have to demagnetize the CT after this test. The standard, the IEEE standard C37110, recommends that you demagnetize after this test. Now, this is why we mentioned demagnetization here, because the demagnetization procedure, if you don't run it after the winding resistance test, then the results of the rest of the test will be affected by the fact that the CT core is magnetized. The demagnetization is used, well, to eliminate the effect of residual magnetism. You can use a variable AC source to ramp the secondary voltage, and then all the way to beyond saturation, and then bring it back until you bring the voltage back to zero. Ideally, you want your CT to be here when you demagnetize it. Other ways of doing demagnetization include using a constant voltage. Okay, the first one we mentioned, or the one that we mentioned in the previous slide, was using a variable voltage and constant frequency. You could also use a constant voltage and variable frequency owing to the magnetic characteristics of the material and the fact that the amount of flux that circulates on the material depends on the ratio of the voltage and frequency that you're injecting into a magnetic material. Or you could also use an alternating DC current in a way that you create an effect similar to that of an AC waveform. In any case, the idea is always to go up and then bring the CT back using a cycle until you are finally at a place where you have no remnants or no remnant flux on the CT. Now, I want to talk a little bit about what an ideal CT would be, or the equivalent circuit of an ideal CT. I tried to make it simple, but not too simple, because I'm going to connect this ideal CT with what would be the real equivalent circuit of the CT. The main difference between the ideal and the real would be the fact that on an ideal CT, you do not have any excitation current. And what that means is that ideally you would have that the ratio of the current in the primary to the current on the secondary equals exactly the turns ratio, because you have no excitation current. That also means that the primary current divided by the number of turns equals the secondary current, and there is no phase deviation. Essentially, the current here, IP divided by N, equals IS. There is no IE. In a real CT, you do have an excitation branch. Now, this excitation branch makes it so that instead of the secondary current being equal to the primary current, the secondary current is now going to be actually the primary minus the excitation. So in a real CT, you have the primary divided by N equals IS plus IE, which means that in a real CT, this IE constitutes an error on the measurement. And as we can see here on this phasor diagram, now we have the primary current, but then we have the excitation current, and then the secondary, the actual current, the current that is going to circulate through our load, which is constituted by our meters, our relays, etc., is going to diverge from the actual image that we want to see of the primary current by as much as the excitation current, and there will also be a phase deviation. You can see from this equation that I have derived here that the excitation current is actually going to be dependent on the load that we have connected to the current transformer. The conclusion from this slide is that the current that you get on the secondary is going to be slightly different from the meter current from the primary, and the difference is the excitation current. The higher the excitation current, the higher the error, and the excitation current is directly proportional to the burden connected. What I'm trying to say is that all conditions the same, a CT with higher burden will have a higher excitation current, and therefore will have a higher error on the measurement. Now, how do we measure ratio on a CT? To measure ratio on a CT, well, it is a current transformer, so we could take a variable current source here, inject current on the primary, and measure the current on the secondary, and the ratio would be the ratio of the primary to the secondary current. This would be, let's say, a very accurate way of doing the measurement. The problem with this is that you would need a high current source to inject that current into the primary, and high current sources tend to be difficult to come by, expensive, big, and not as easy to operate as an alternative measurement method that we're going to present here, which is the voltage method. Now, on the voltage method, you would still have a alternating source here, but in this case, it would be a voltage source. We do not need as much current to circulate, because in this case, we would be injecting on the secondary. Remember, in the previous case, we were injecting current on the primary. Now we are injecting voltage on the secondary. Why can we do that? Because we know that in a transformer, we can approximately say that the ratio of the voltages equals the inverse of the ratio of the currents. Now, I'm assuming here a no loss transformer, but since we are injecting voltage on the secondary and the impedance of the secondary is very high, then we can take this ratio of the transformer as being the inverse ratio of the voltages. The ratio in this case would be V2 divided by V1, or the voltage that we're injecting on the secondary divided by the voltage on the primary. The excitation or saturation test, we use the same connections that we had here. We inject variable voltages. We start by injecting low voltages and measuring the currents. Here we have this voltmeter and ammeters, which allow us to inject higher voltages and then measure the currents. We can do it for a multi-tap CT. We can do injection on the outermost or bigger taps on the CT, or the main taps of the CT, and then we can measure all of the taps at once. My colleague Mike will show how we do that with our instrument. These are excitation curves on a multi-tap CT, where you can see that here we have a straight line showing the knee point that we are going to show next. Now, the knee point on a CT, according to IEEE, you would define the knee point for non-gap cores as the point where the tangent, and you can see here the tangent is this straight line that we have here, that touches the curve is at 45 degrees with the horizontal. Now, as the curve is drawn, you have multiple tangents. At some point, this starts moving into saturation. When it starts moving into saturation, this straight lines start changing their angle. When that angle becomes 45 degrees, you say that that is the knee point of the transformer. If the current transformer has gap cores, then instead of being 45, you make this 30 degrees, which means that for gap cores, that straight line will be somewhere like here, what you can see from the cursor. Now, I want to say one thing about the knee point. The knee point is not the point where the transformer saturates. Actually, the knee point voltage is normally around 46% of the saturation voltage, which is something that you can use to avoid saturation on transformers by properly, configuring the burden that you connect to them. See how the knee point is here, and if we go all the way down, the transformer is actually deeply in saturation. When it gets to this point here, this is when the transformer will start presenting, let's say, non-asymmetric saturation. And see how the difference, in this case, we have about 280 volts, and the real place where the saturation is actually completely declared on the transformer is around the, let's say, 500 or 600 volts mark. The problem is that we see these graphs. It is a logarithmic graph, but we interpret it as a, let's say, linear graph. So we think that the difference between this point and this point being so close in the graph is very small, but it's actually very big. There's more voltage between this point and this point than the voltage between the start and the point where the saturation knee point is declared. So polarity. The polarity is, relative instantaneous. We can go over all of that, but the reality is that the easiest way to see it is that if the current on the primary goes into polarity, then the current on the secondary goes out of polarity. That's the easiest way to see it. Schematically, we would see it something like this. We have our polarity points here, our polarity marks. We have H1 and X1 on this transformer. If the current goes into polarity, that means that on the CT, it has to go out of polarity. Correct? Now, how do you measure polarity? The easiest way to measure polarity is by measuring the phase angle. We have the same connection that we use for the ratio and for the saturation curve, and we somehow find a way to measure the phase angle on the current transformer. Now, the burden, the burden on the current transformer is that load that is connected to the secondary of the current transformer. Remember, from here and looking to the left, this is the current transformer itself. This would be the primary, this would be the excitation branch or the excitation impedance. Then you have the leakage and the current and the winding resistance. The leakage is something that depends on the type of transformer that you have, etc. In some cases, it's very small. In some cases, it's significant. This is the leakage of the secondary winding of the transformer. Now, the burden is whatever load you have connected beyond those terminals, whatever load you have connected to the terminals of the winding transformer. I'm sorry, of the current transformer. Now, for the burden test, remember you are not testing the CT, you are testing the load, not the CT. Therefore, disconnect the CT from the circuit, as you can see in this diagram here. My colleague Mike will show you how to perform a burden test with the CT. For the burden test, what you do is you will inject an AC current into the load of the CT. Now, that load is made of all the relays and meters, etc., plus the wires that bring that connection from the CT into the into those meters and relays, etc. The burden is expressed as either VA and power factor, or that's the total impedance with respect to both resistive and reactive component. Now, after we talk about burden, let's talk about accuracy class on CTs. And I just want to mention the most common accuracy class out there. We could be talking about accuracy class for a long time, but I want to talk about the most common relaying accuracy class, which is the C designation. Now, this one requires a maximum limit of ratio error at 20 times rated primary current of 10%. And the C designation is followed by a number, which is a secondary terminal voltage that the CT will support while meeting the error limit. What does it mean? Let's use the C800 CT as an example. This means that when the terminal voltage on the secondary of the CT is 800 volts, at 20 times nominal, the nominal current of these CTs is typically 5 amps. That means that when the secondary current on the CT is 100 amps, you have to guarantee a primary error on the, an error on the primary current of 10%. What is the burden connected in that case? Well, if you have 800 volts and the current circulating is 100 amps, the burden will then be 8 ohms. That means that all you need to know from this CT is in the designation. C800 means that at 800 volts terminal voltage, when the current is 100 amps, I'm going to have a maximum of 10% error. And what's the allowable load in this case? 8 ohms. It cannot be any higher. Lower loads, you have lower error. But if you have a load higher than this 8 ohms, remember that we showed an equation where we connected the excitation current with the burden, and how we showed that the excitation current constitutes the error. Therefore, if you have a higher burden than this 8 ohms, then you will have an error higher than 10% at 100 or 20 times nominal, which means that you cannot use that CT for that application. The standard secondary voltages and burden shown on the IEEE standards go from 10 to 800, and as you can see here, the burden tables show that this is 0.1, 0.2, 0.5, 1, 2, 4, 8. Remember how we connected this 800 with this the C800 CT, and we said that the burden was 8 ohms. This is what it means. If you have a C400, the maximum burden is 4 ohms. If you have a C10, the maximum burden is 0.1 ohm. Now, you have different burdens for relaying and metering. Typically, you will have lower burdens allowable for metering because you need higher accuracy, and you have higher burdens for relaying. And here is a table from the standard that shows resistances, inductances, impedances, total power, and power factor for each of these applications. You also have here the metering class CTs, the metering accuracy classes, and for voltage transformers and current transformers, which is what we are talking about right now. at 100% rated current or at 10% rated current. Now, let's connect the dots a little bit. We said that at 20 times nominal, we were going to have 800 volts. That means that what you have to do is you come to the saturation curve, 20 times nominal is 100 amps. Now 100 amps, the error on 100 amps is 10, which means that you would have an excitation current of 10 amps. You connect this to this point here, you look to the left, and this would be the allowable voltage at 20 times nominal for a 10% error. If you had 5% error, then you would come to your 5 amps here, because it's 20 times 100, 5% is 5, and then you would see here that your allowable error would be here on the left. Now, the error limits for CTs type C, which is the only one that we have talked right now, is 3% at rated and 10% at 20 times nominal. Other classes we haven't discussed, so we're not going to go a little any deeper into them right now. For metering, you have this, we call it the ANSI parallelogram, where you have a representation of the allowable ratio correction factor and the phase angle deviation, and you can bring your CT and locate it here, depending on what's your phase angle deviation and the ratio correction factor for the load that you have connected, and you can locate your CT. If the CT is inside this parallelograms, you're good. If it's outside, you're not. You have here an explanation of what this means for different accuracy classes, for example, 0.6, 0.3, etc. I wanted to mention that for metering CTs, you have high accuracy classes, which are mentioned also in the standard. We will send this presentation out, but you can go there and find them. Essentially, what I mentioned in my first slide is that CTs for metering have to guarantee an accuracy between 10 and 100% of nominal, but there are other accuracy classes that have to guarantee a higher accuracy at different levels of rated current. For example, this one goes from 5% to 100% with 2 different accuracy classes, and this one here, for example, the accuracy class 0.15S has to guarantee 0.15% between 5% and 100% and 150% of nominal. And then you have the high accuracy extended range, where it has to guarantee the accuracy between 1% and 150% of nominal, which means that this is a CT which a much more stringent accuracy requirements than the typical. Now, this is now possible because manufacturing methods of CTs and magnetic materials, etc., have made it, let's say, easier to manufacture such high accuracy CTs. It is also required for different measurement applications. Now, I wanted to, at the end, present the phase angle minutes and curves. This is a typical phase angle curve that you would see for a CT, and these curves are presented for a particular burden. If you have more than one curve in one of these graphs, it means that it's a curve that is presented for a different burden. If you had 2, one would be presented for 4 ohms, but the other one would be presented for, let's say, 8 ohms or something like that. Now, these curves are presented as the phase angle deviation at percent of rated current. So let's say that I want to know what is my phase angle deviation in minutes at 20% rated current. I come here to this number 20, and I come to the graph and I see that I have 5 minutes of deviation. At 100, I'm expecting, if this is a CT, that 100 would be the best number for my accuracy. So I come here at 100, and I look at my phase angle minute, Mike will present you the curves that come out of testing a current transformer from our instrument. You also have these same curves. They call them typical, I'm sorry, they call them ratio correction factor curves, and it's the same thing. At different percentages of rated current, what is the ratio correction factor that I have to use? Remember, I'm not gonna have zero error, but I can use these curves to know, depending on how much current is circulating, what is the correction I have to do to my measurement in order to make a measurement as accurate as possible. With today's meters and relays, you can actually use this information to go into the meter or into the relay to program those curves there and get a much more accurate measurement, even with an inaccurate CT. That means that you don't have to replace a CT all the time. Even an older CT, you can go into the CT, perform this test, get these curves, and go back into your meters, program those curves there, and those curves will allow you to have a much more accurate measurement with even an inaccurate, let's say, CT, because you know what the errors that you're expecting are going to be. Now, the standards that we have for current transformers are presented here. We have the C5713 standard requirements. We have one for field testing of relaying current transformer, and then we have the IEC standards down here. As a summary, we have presented tests for current transformers. We presented the insulation resistance, winding resistance, saturation and excitation, ratio and polarity, burden, and CT demagnetization. And now my colleague, Mike, is going to do a hands-on test on SCT. So Mike, go ahead.
Okay, thank you, Abel. It was a very good explanation. I will now proceed with demonstrating the use of Power DB Lite for testing a 5-tap CT with MEGGER's MRCT test set. We will not be testing a VT or CVT today, just a CT. So we'll get started by going into the settings screen. We'll start with the user information. Now, I've already entered some information just to save time for today. In the user information, start with the customer. If you own the equipment, you probably just put your own customer, your own company name here. If you're a testing company, surely you would put your customer here. The address, the name of the station, the location and they sometimes can be used differently by different companies. The important thing here is that these two fields combine to tell you exactly where this piece of equipment is. This possibly would be the number of a transformer or a breaker located within the station. This might tell you what bay it is. If it's a smaller breaker, it might tell you what cubicle in the switchgear it is. Clearly, you'll put your name in to document who ran the test. And as always, temperature and humidity are good things to document. Okay. Going into the nameplate of the transformer, you'll see here I've got 6 CTs configured. This is simulating a theoretical breaker, 1 CT on each pole. However, we can test up to 18 CTs with a single test result. 18 has shown itself to be sufficient number to test almost every transformer or breaker in the field today. Can't say there's not some exceptions, but so far this has worked out very well for us. Okay. Number of cores. This is primarily used for auxiliary CTs. Auxiliary CT may have a common primary and multiple secondaries. Okay. Number of taps. This is the number of taps in a CT. A single ratio CT would be a 2-tap, which would be X1 and X2. The most common CT you're likely to see will be a 5-tap, though as you can see, we're flexible to test almost anything in the field. CT label. CT label can be used in different ways, but the preferred method is you stay by the standard CT location terminology, with X CT being the closest to the bushing cap, Y being the next one down the stack, and so on. CT name. we defaulted to CT1, 2, 3, 4, etc. However, you probably would want to change this to either be the designation in the user guide for the equipment you're testing, or possibly the nomenclature from your 3-line. Or your company may have some other standard they would want you to use. Okay. Document the manufacturer of the CT, the serial number of the CT. If this is an oil-filled piece of equipment, the CT is not going to be accessible. Even if it's a vacuum breaker, it might not be easily accessible. So if you don't have the serial number, you might be able to get that from the bill of material or the other documents that came with the equipment. The asset ID, this comes by your company policy. Some companies would require you to have a separate ID for every individual CT. Other companies may have you just document the ID of the equipment it's connected to. Just know your company policies here. Obviously, you're going to designate your phase. You get this possibly from your 3-line or from any other phase markings in the station. If the CT is in a transformer and it's buried in a delta connection, put a check mark here and we'll perform the correction ratios for you so that it reads the correct ratio following the test. You have to choose whether it's a metering or protection class CT. If it's metering CT, you choose your correction factor. Your saturation standard, your accuracy class. You choose your burden. The VA is calculated for you. However, all of this information is on the nameplate of your CT, so you would want to verify that with your nameplate. Okay, I'm actually testing a C20 today. And again, the VA and the burden many times will be on the nameplate of the CT if you can see it. The actual burden in VA and power factor would be acquired by performing a burden test. If you have that information, it's a good thing to attach it here. Okay. This is your service tab. This is more for documentation purposes than anything else. You install the ratios of your outside taps. In this case, it's a 600 to 5 CT overall. So we have 100, 150, and 400 as our ratios. When all this is complete and you're ready to go to the next CT, there's no need to enter everything from scratch. Just simply copy from nameplate, CT1, and now correct anything that needs to be corrected. This is already defaulted to CT2. I've put it in B phase here. Everything should be good. So you would proceed across. When you get to the other side of the breaker, you would do the same thing. It may be a different ratio, so you would want to be careful with that. It's probably A phase still, but now, because we're on the other side of the breaker, we can put a check mark in simulated primary lead swap. This will prevent you from needing to climb the ladder and move the leads around. Okay, so we will explore more about the home screen in a little bit, but for now I'm going to show you just how quick and easy testing a CT can be. We're going to do a run all test. I'm going to do all saturation, all ratio, and all winding resistance. You do have the option of only testing the ratios as expressed to X1, but it doesn't take any longer. It takes the exact same amount of time to get everything, so why not do that? Press the play button. You're going to get your standard connection diagram up, and I'll come back and discuss this a little bit more in detail later. I'm going to press the play button, and the test is running. Okay, so the first thing it's going to do is DC winding resistance test. You can watch right here. As it applies current, it's reading voltage. You'll see the current building slowly. It's beginning to ramp down, so the test is coming to a conclusion soon. Okay. There's your result. Okay, you didn't really have time to read it, but that's okay. It's all being put in the test report for you, so there's plenty of opportunity to see it later. Okay. Now we're demagnetizing the CT. Remember, Abel explained that anytime you magnetize it with a DC current, it must be demagnetized before proceeding. And what you're seeing here is just a representation of what's going on with the CT. It's being driven into saturation for just about a moment. I heard it buzz just a little bit, which is normal. Okay. Proceeding with the test. And now it's beginning to ramp down, slowly desaturating the core. Just a little bit longer. And we're almost done with this one. And there's no test result associated with the demag. It's just a procedure. Okay. Now we're going to do the excitation curve or saturation curve. Okay. You see we're accumulating all the data points simultaneously. The test set is actually taking reasonably large steps in voltage as it's beginning to watch for the beginning of the knee point. When it reaches the beginning of the knee point, it's going to slow down and start taking a higher rate, a higher sample rate to collect more accurate data through the knee. And now it's going through the knee and it's entering saturation. Notice it's saturated at about 42 volts if you were watching. Okay, now it's ramping down. The reason it's ramping down slowly is you don't want to ever turn it off at the peak of a waveform because it would leave it saturated again. So you want to slowly reduce voltage to be sure that you do not saturate the CT. Magnetize the CT, excuse me. Okay, now it's finally testing the ratio. Okay. Still taking note that we're reading all voltages at the same time. There's multiple voltmeters built into the MRCT, so we're taking a lot of data points very rapidly. Okay, okay, and we're done. That was a little bit under 4 minutes, about 3.5 minutes overall. Okay, so now you can look at your test result. Here's the information we put in to begin with. Okay, we have our CT information here. The fact that we're using ANSI 45 saturation standard. Here's the nameplate ratios that we entered. These ratios are calculated for us in the background. All the measured ratios, percent error, everything looks very, very good. Proceeding on over here, you have test voltage, test current, the primary voltage red on the high side of the CT, the information regarding the knee point. Now phase deviation, polarity is showing to be correct. Resistance in ohms, that's DC resistance. And then the DC resistance as it's been corrected to 75 degrees. Okay. Now we have our excitation curve. You can see all the ratios are independently represented. If you want more information about this, you can display all the data points taken. Go to page 2, and you'll see that we took 24 data points on every winding selection. Okay, there's really no need to leave that up. It can be exposed at any time if you desire. Okay. Now we'll get into the ratio and phase error. This is all collected on X1 to X5. The chart showing the ratio error in percent and at rated current is supported by the top graph. This is your rated current. This is your burden, your VA, and all of these data points come down to make up this correction factor. Now notice that you're going to be more accurate as you get above, as you get around and then above the nominal current of the CT. 100% rated current right here, and here's 200%. Okay. Phase displacement in minutes of rated current. This is what we're using to populate the graph for phase displacement, rated current. The same information is presented here. Now again, this is not degrees, this is minutes of a degree. All of these data points combine to populate this chart here. Okay, and then the final assessment, everything passes. So that CT has been properly tested. So now we're going to go back out to the home screen. Now everything that we've just done, you can do individually. You can individually do a DMAG if you have a concern. There are times when things don't go well. Perhaps the circuit breaker trips while you're testing, and it's possible that you interrupted a CT while being tested, and it could very well have been near the peak of a waveform. It might be a good idea to go ahead and demagnetize it here. You can do an individual ratio, saturation, winding resistance. You're going to look at the burden test a little bit closer. Okay. Burden test, you select the current in DC amps that you want to apply. I can't actually run the test because I'm not connected to a circuit, but I do want to look at the connection diagram. And I know Abel already mentioned this one time, but take note that this is actually not connected to the CT. It's connected to your relay circuit. It's actually right here. This is your relay circuit. Keep in mind that we're applying an AC quantity to your circuit, and that means that you're going to be possibly operating neutral relays, ground relays. If you're in a live station, if this is a retest, well, then you certainly want to be sure and secure your trips or do whatever is required to not do damage in the relay house, and be sure everyone is clear in the relay house. Okay. And I'm going to cancel that since I can't run it. And go back out to the home screen. Okay. You can also do a quick manual test, which we will do here. Okay. I'm going to choose CT3 just because it has not been defined. And the reason that you might want to do a manual test is if something has transpired and you just need a quick answer just to confirm a ratio, or something quick about your CT. You can do this without putting any nameplate information. If you know what the ratio is supposed to be, you can just take control of it and do it very quickly. So to do this, you would need to select a tap. I'll select 1 to 5. You need to select a ramp rate. Auto ramp rate means that the faster you try to ramp it, the larger the step it will take. I personally prefer to have a definite step. A half volt per click on the wheel mouse will be a little bit coarse, but it'll also save time for today. Okay. So now when I'm ready to test, I can just turn it on here. Okay. Now this is telling you what you're testing. And I want to point out a couple of things about this connection diagram. First of all, the primary cable is a shielded cable. That shield needs to be grounded. We've given you a place for the ground here. Just plug it in. Secondly, notice that the black lead is labeled H1. It's a little bit unusual, but there's a good reason for that. To ensure accuracy and give high performance, we needed to ground H1. We didn't want to ground a red post, so we made H1 black. The cables are marked well, should be no confusion. Okay. The other thing I want to take note of, we're doing a single ratio test when we're testing manually. And I am testing 1 to 5, but I could have selected 2 to 4 if I had chose. We would still be testing with X1 and X5 on the test set, even if we chose 2 to 4 out here. The reason for that, X1S, X5S, the S stands for source. So we're actually placing the voltage on the CT as close to the CT as we can. Now, most times that's going to be at a terminal block in the control cabinet. In a transformer, there's still a significant amount of wiring up to the CT. There's really nothing we can do about that. but we don't want to introduce any additional error with test leads. So we're actually measuring the voltage at the terminal block as close to the CT as we can get. If you're doing a single ratio, it doesn't matter what taps you're selecting, you always would be using X5 and X1. It is possible to set your configuration to disable these connection diagrams. It's really a good idea to leave that turned on so you always get a representation of the connection itself. Okay. So now I'm going to press play. Okay. And the test is going to begin shortly. Notice it says that I can save up to 14 points manually. What this means is that you can do a manual excitation test if you choose. So I'm just going to be running voltage up a little bit. We've already determined it's a 605 CT. So if I'm looking for a quick ratio answer, I've already got it. No need to do anything else. But I want to go ahead and show you the manual excitation test. Now this should saturate just a little bit over 40 volts. So I'm going to continue to roll it up slowly, begin watching the current, and I want to watch for a small increment in voltage causing a high increment in current. And that indicates that we're passing through the neutral point. Okay, getting closer now. One or two more. Yep, it's beginning to go through saturation. Okay, I'm going to save one data point here, right here. I'm going to come down 1 volt. I'm going to save another one. Come down 1 more volt, save another one. And we get 14 data points that we can save. If you're doing this manually, you have to be mindful that you only get the last 14 clicked. So if you try and have too much resolution on the bottom end of the curve and you start chopping off some of the first data points taken, you might actually start losing this point of the display here. Come on down a little bit more. You can see now I'm getting back into the linear portion of the CT. A little bit closer. And I'm going to intentionally get a 15th point and pay attention to what it does right here when I do that. Okay. There's my 14th point. So now I'm actually going to take off a little bit of this above the knee point, and that's okay. It doesn't have any way to tell me any kind of error correction because I didn't tell it what the CT is. I chose one from the nameplate that I did not yet configure. When you're happy with this, turn off the test, and this is now added to the test result for you. And that concludes the demonstration. And so I will be turning this back over to the moderator.
All right, excellent. Thank you very much. So at this time, the presentation portion of the webinar has officially concluded. We're going to take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's also a field where you can request a demo or a quote on any MEGGER product. A copy of the presentation along with a link of the video recording of the webinar will be emailed to everyone in about a week. You can also view video recordings of previous webinars on our website at us.megger.com/webinars and register for next week's webinar, Practical Considerations for Low Resistance Testing. The presenter will be Samir Kulkarni. So let's jump into the questions. The first one's going to be directed over at Dinesh. What voltage should we apply in order to test insulation resistance tests, such as high voltage to low voltage, high voltage to earth, and low voltage to earth?
Good morning, everyone. So the question is obviously on insulation resistance on CTs, and typically to be on the safer side, MEGGER recommends to apply no more than 500 volt or at max 1000 volt for this testing. And the reason for that is that when you look at the secondary winding, you have very few number of turns on it, and also the insulation may not be rated for very high voltages. The other thing that you need to keep in mind is that a lot of time on the primary side, it might be just the center conductor. So to perform this test in a safe manner, the recommendation is to use 500 volt or 1000 volt when you're performing high to low, high to ground, and low to ground test.
All right, thank you. Daniel, our next question is for you. If my CT got saturated already due, let's say, by fault in the line, then can it be demagnetized and made to work properly, or should it be replaced considering it's a protection CT?
Okay, good morning, everybody. So interesting question. Yes, for sure, if you have the suspicion, right, that due to a fault, the CT can be magnetized. I mean, a good practice would be just to confirm, right? You can do both saturation and ratio measurements to make sure that that is the condition. And then for sure, as Abel explained during the presentation, typically a test instrument, a CT test instrument, will have a dedicated process, right? An algorithm to be able to demagnetize a CT. So just for sure, it's recommended to run that process and then again retest both saturation and ratio to make sure that the process worked. And yeah, considering the CT is no damage, you can put it back in service.
All right. So Dinesh, what is the difference in magnitude between knee point voltage and saturated voltage?
That's a very interesting question. So if you look at the definition of knee point or knee point voltage, it is a point on this excitation curve where the CT starts to saturate. And then the question is asking what's the difference between the knee point voltage and the saturated voltage. So when you calculate the knee point, you're just looking at that. If you're using ANSI standard, you're looking at the tangent at 30 or 45 degrees. But when you're looking at the saturated voltage, you are talking about way on the right hand side of the curve, where you are looking at the CT when it's completely saturated. And I will try to explain this a little bit more. You know that for a protection class CT, it is defined as that you should be able to get a good ratio measurement up to 20 times the rated secondary current, and the error should not exceed more than 10%. So if you take 20 times of 5 amps, which is the rated secondary current, it's 100 amps. And if you think about the 10% of that, that's 10 amps. So if you truly want to know what is the saturated voltage, you would have to drive the excitation curve all the way to 10 amps, which is the x-axis. And then you try to look at the voltage corresponding to that 10 amps on the y-axis. That would be your saturated voltage. So again, knee point is the point where the CT just starts to saturate, and the saturated voltage is the voltage that you would get typically at 10 amps of the excitation current.
All right. So Daniel, next question's to you. What is ALF of the CTs and what is ISF?
Okay, both design considerations, right? And these are indications you will find on the nameplate, depending on the CT type. ISF, right, meaning instrument safety factor, is for metering type CTs. And this has to do, remember, whenever I went over the differences between the two, right? On metering type CTs, you expect to not have large faults in the system, right? The CT should be really accurate across between 0 and 100% of the rated current. So these safety factor will have to do when in the case there is a fault in the system, and depending on the factor, that CT will guarantee that devices connected to the secondary are protected whenever that condition is met. In the case of ALF, right, indicating the accuracy limit factor for protection type CTs. And similarly, in this case, the CT is actually designed to be accurate, right? Even when the primary current is many times the nominal or the rated current of the system. So this accuracy limit factor will indicate where is the limit, right, for that level of primary current being higher than nominal to guarantee the accuracy of that particular CT.
All right. So, Abel, what are the most important items do you have to take into account when you are going to choose an application of CT?
Okay. Well, the most important items you have to consider, well, the first is the primary current that you want to measure. You would choose a CT that can give you a measurement within the rated nominal of the secondary, and that does not exceed that that measurement. That would be the, I would say, the first element. The second element is how much accuracy do you want? Is the application for metering? Is the application for protection? Is the application for both metering and protection? Given that you can find CTs out there, actually most of CTs you can find out there in the market right now can be let's say specify that they have both a specification for metering and protection. And the third one is how much load are you going to connect to that CT? The same CT for different loads. You may have to, if the load is too high, then maybe you have to select the CT with a higher ratio. So I would say those are the three main elements that you have to consider. How much current are you going to measure, what the application is going to be, and what's the load that you are going to be connecting to it. That's not talking about voltage levels and things like that, that I'm not, I'm putting out of the question in this case. I'm basically basing my answer in the characteristics, the metering characteristics of the CT.
Good deal. So, Dinesh, how often do metering CTs need to be tested according to IEEE?
So there is no straightforward answer to this one, because if you talk about IEEE standard, they don't have a recommended timeline on how often you should test CTs or metering CTs. But the way I would like to answer this question is that whenever the metering CTs are used for revenue purposes, obviously you want to make sure that it is reading accurately, and you want to make sure that it is a true reflection of the power being consumed. One of the things that comes up quite a bit on the metering CT is that people are mostly interested in the ratio and polarity. If you truly want to find out the accuracy class of the CT and how truly accurate it is, you need to run a test, what is called as the ratio error test, in which you would generate the ratio error tables. And in order for you to generate the ratio error tables, you also need to run the saturation curve. And from those ratio error tables that Mike showed, both for phase angle error and ratio error, you would be able to generate a parallelogram. And with that parallelogram, you would be able to find whether the CT meets the certain accuracy class or not. So when it comes to metering class CT, we recommend it to test based upon the application in which it is used. And also, whenever you run the test, you need to run the ratio, polarity, insulation resistance, winding resistance, and the saturation curve to truly identify the accuracy class and accuracy of those metering class CTs.
All right. Abel, why is the burden in protection CTs higher than in metering CTs?
Michael, before answering that question, can they see my screen now?
Yes, we are on slide 21 on our screen.
Slide 21, perfect. Well, the answer to that question, I would say we could talk about many different parameters, but the answer comes straight from this equation that I'm showing down here. Let me, I don't know if you see it, IE, the excitation current equals a multiplication of the primary divided by the ratio times the impedance that you have connected to the CT. Now, the impedance in this case is mainly the burden plus the wires that you have connected to the CT. You can see here the error on the CT is made mainly of the excitation current. Now, the excitation current has a direct relationship with the burden. The higher the burden, the higher the excitation current, and hence the higher the error. On a metering CT, you want high accuracy, and therefore, if you're looking for high accuracy, you're looking for as small an error as possible. And if you're looking for as small an error as possible, and the error is directly proportional to the burden that you have connected to the CT, then the conclusion is that for metering, you need to have as small a burden as possible. And that's why metering CTs are classified, as a small burden, a smaller burden than the than the burden that you allow for a protection CT. A protection CT has usually, always a higher error allowed than the metering CT. In the metering CT, you're looking for accuracy over all the range. You're using metering CTs to charge people money. So you want to be as accurate as possible. On a protection CT, you're looking for the ability to measure over a wide range of currents. And in your protection schemes, you protect yourself against the inaccuracy, the inherent inaccuracy of that measurement. Because when it's most important for the protection CT to measure is when the current is a lot higher than the current in the system, the nominal current in the system, which on the other hand is when the metering CT is most importantly to be accurate. So since the let's say accuracy requirements for a protection CT are not as stringent, then you can allow for a higher burden, a higher error, given that, and you're looking for the ability to measure at those higher currents. I guess that would be the answer to it.
All right, awesome. Dinesh, so next question is over to you. If you have a CT class with a sum of a VA of a load, you can change the accuracy when you load it in with a short value under what of a nominal value?
Okay, Abel, if I may request to stay on this slide.
Okay.
So the answer to answer to that question lies on this slide. As Abel mentioned in his presentation, that the error in the CT measurement come from two parameters. One is the ratio error, other is the phase angle error. And if you look at this slide, you would notice that the error is coming from the current, which is in the excitation part, IE. And if you look at the equation of the IE, the burden is part of that equation. Now, whenever a CT manufacturer defines a certain CT, they would say that as long as the burden is of such and such value, I would maintain this much accuracy for the CT. It's just that you should not exceed that burden rating. But imagine if you lower the burden. If you lower the burden, you can see that you would lower the I excitation current. And if you lower the I excitation current, obviously your error would reduce as well. Now, keep one thing in mind, that this is mostly applicable for the metering CTs, because they need to be highly accurate. The moment we start talking about the protection class CT, then it's a slightly different talk, because now you're talking about the CT saturation, 20 times the rated current and all that stuff. But the explanation that I just provided is truly applicable for metering class CT, because if you can lower the burden rating, it would impact the excitation current, and if it impacts the excitation current, it would certainly impact the error associated with that CT.
All right. So Daniel, the next question's over to you. By simple earthing, why can demagnetization not happen?
Okay, to answer this question, I guess we first need to understand why we would get a magnetized core in my CT. So in practical terms, we can say two main scenarios, right? In service, that would happen if a large primary current circulates, right? And that is obviously in case of a fault. In testing terms, right, we can magnetize the core either while running a saturation excitation test, or whenever we are testing with any DC quantity, either DC voltage or DC current, like when we measure winding resistance, right? We are practically aligning the atomic dipoles in the core of the CT, right? So in order to revert that state, right, in order to misalign those dipoles, we need the same effect, but in opposite direction, right? We need a magnetic flux established in the core of the CT. So that cannot be achieved with just earth or grounding the CT itself. So again, we need the same scenario as that caused that magnetization, but again in opposite direction.
All right. So Abel, how can we calculate the saturation voltage to verify the value we obtained in how we calculated the saturation voltage when we've verified the value obtained in the test?
Okay, depending on the type of CT that you're testing, and that's very important, what class of CT you are testing. There are equations out there by the CT manufacturer that you can use to calculate most of the parameters of the excitation curve. In other types of CTs, you cannot. You have to determine that by test. Ideally, you would have a reference test with you, and you would compare that reference test with the result that you obtain in your test to see if the magnetization curve of the CT has or has not changed. However, I want to stress something, and this is very important. The most important thing in a CT is not where the knee point is and where the saturation point is from this curve that we get here. Why? Because the most important thing is, where is the CT connected? What is the CT connected to? What is the burden on the CT? Why is that so important? Remember how the excitation curve, the excitation current is going to be directly proportional to the burden? Well, here we have, in this curve, we have the secondary exciting amperes, which is the excitation current, right? So for a given excitation current, we can come to this graph and see how much voltage I can allow in order to stay in the linear part of the characteristic. So if I have the excitation current and I know the burden, then I can know where in this curve I am going to be, and I can decide whether my CT is operating correctly or not for my application, regardless of whether I have the CT saturation curve or not. Let's say I go to a CT, I know nothing of it, I take this saturation curve, I get my burden, and with my burden and my application, I can know whether with that burden I have proper operation or I'm not going to have proper operation. All right. So I would say, if you want the saturation point, maybe you can get it from the manufacturer. There are equations out there for some types of CTs. They're very complicated. They need a bunch of parameters. Maybe you can get the curve sent to you from the manufacturer. They all have them. Okay. But let's say you don't have that because your CT maybe it's too old or the way you got it, I don't know. You can always do this. You can run the saturation curve, do the burden test, and determine what your error is going to be for your particular application. You can use our error curves from the MRCT to determine if your CT for different burdens is going to, fulfill your. I think that's the most important part. Not exactly knowing when the CT is going to saturate in general, but if the CT is going to saturate for my application, which you can get from this result and from the burden that you have for your particular test.
All right.
Sorry, Michael, I finished.
Yeah. Okay, no worries. So Dinesh, the next question is going to be for you. By how much is IEEE knee point different to IEC knee point?
Okay, that's a very good question, and this question gets asked quite a bit. Both IEEE and IEC use different method to calculate the knee point. IEEE has the option of using NC45 or NC30 slope line. So you draw a tangent to the saturation curve at an angle of 30 degrees or 45 degrees to determine the knee point using the IEEE method. Whereas the IEC calculates the knee point based upon the fact that for a 10% increase in voltage, the increase in excitation current should not be more than 50%, or it should be 50% increase in current for a 10% increase in voltage. That's how they determine the knee point. So the method of calculating the knee point is different for both IEEE and IEC standard. That's why you might see a little bit of difference in the knee point if you run the same CT with two different methods. In our instrument, you have the option of selecting either the IEEE method or IEC method. And with that one, you can see how much the difference is. But again, as I said, like the method is different to calculate the knee point, so you might see some variations.
Okay. So Abel, can a saturated CT be used for measurement purposes until a replacement is available?
I don't recommend doing that. The answer is, the reason is that you are going to get poor results not only on the magnitude, you are going to get poor results on the phase, and you will probably, depending on how deeply saturated the CT is and how hard the magnetic material is, you are going to get deformation on the curve that you get on the other side. Remember that all our metering and protection systems are based on measuring sinusoidal waveforms, sinusoids. Now, when you have a saturated CT, at some point, you stop getting a sinusoid on the other side. You start getting a very, let's say, deformed waveform. So not only your magnitude and phase are going to be wrong, probably your the waveform that you're getting is not going to be a properly formed sinusoid. So even though you could get measurements on the other side, and depending on the degree of saturation, which there's no way for you to know ahead of time, you could, but I really don't recommend using a saturated CT to perform measurements or protection.
Okay. So Daniel, when testing CTs on a power transformer, does the residual flux captured in the power transformer's core cause errors? And if yes, how do you correct those errors? Does one need to demag the power transformer core?
Okay, so on the first section, right, when you are doing ratio, when you're testing ratio on a CT, that's on a bushing on a transformer, yes, you do need to worry about the effect of the windings of the transformer affect your results, right? So in order to get rid of those effects, you have to perform certain connections depending on the configuration of the transformer you're testing, right? Typically on the other side of the transformer of the where the CT is located, you have to short those windings. And again, depending on the configuration of the windings on the side of the CT you're testing, you need to make some arrangements. Typically, you have to jumper a couple bushings. Again, it depends on the configuration, right? You don't need to worry about demagging the transformer core, but yes, as it's been mentioned many times before in the presentation and during questions, you do need to demagnetize the core of the CT you're testing if you run any of the DC related test winding resistance or insulation ratio.
All right. Abel.
Insulation resistance, I'm sorry, it's not ratio.
Oh, no worries. For insulation, okay. Is it possible to conduct the ratio test by current method, Abel?
Yeah, it is possible to do it. We mentioned that on the presentation. There's a slide here that shows you how to do it. However, the reason I'd say if you have a voltage tester, it's easier. Let's say you need to test a 1600 to 5 CT. Supposedly you want to get 5 amps on the secondary. How much you need to inject on the primary? 1600 amps. While it is still done, people still do the test using the current method, because if you have the tool, you know, if your only tool is a hammer, then all your problems are nails, right? So if you have the tool and it's available to you, then by all means. But it is cumbersome. You need to deal with higher levels of energy, high amount of energy. It is dangerous because if the CT during your test, for some reason the secondary opens, or you have some sort of problem and you have an open secondary, we all know what happens. Or well, even if we don't, let me tell you, if you have a secondary open on a CT when there is a high amount of current going on the primary, since the CT has such a high inductance, then you're going to produce a very, 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 very high voltage that can be destructive. So the answer to the question is yes, you can. If you have the tool, by all means, if you know how to do it and you can perform the test, safely, do it. But if the method of testing using voltage is available, it's a lot safer. You're not using as high amount of energy. Here we are using some voltage that's somewhere between 0 and the knee point, and sometimes you're using half of the voltage of the knee or even lower, and the amount of energy that you're injecting is very low because we are only talking about the excitation current at that point. And why would you use the current method if the voltage method is available? So that would be the answer.
All right. I think we have time for one last question. So I'm going to throw this over to Dinesh. How do you test CTs that may have a very high knee point average above 2000 volts?
Thanks, Mike. Before answering this question, I just want to add one other point to the question that was asked before about the current method to perform the ratio test. Yes, certainly you can do it, but as Abel mentioned, that in addition to the ratio test, typically you would do an excitation curve test, which is mostly applicable for the protection class CT. You would also perform insulation resistance. So if you're going to go out in the field and perform these tests, you certainly would need a voltage source to perform those tests. And if with the voltage source you can perform the ratio test as well, then you avoid the need for carrying a heavy instrument, because you know that if you want to inject 1000 amps or 1200 amps, you would need quite a bit of a large test set. And not only that, you would need a great input source, maybe possibly 480 volt source to perform the test. So for those practical reasonings, voltage method is more recommended. Now coming to the question that Michael asked how do you test CTs that may have a very high knee point? Some CTs may saturate at 4,000 volt or even 10,000 volt. So to answer that question, just think about of what is happening when you're doing a saturation test. You are building up enough flux to saturate the CT. And the formula for flux is voltage times time. So as I increase the voltage, you are increasing the flux and you are saturating the CT. If your CT needs a voltage to saturate which is greater than 2000 volt, one of the method that is recommended in the IEC standard is to use DC voltage. And the way it works is that the area under the wave shape, if you look at the sine wave, the area under the wave shape is basically a representation of flux. So if you apply a DC voltage and do the integral of the area under the DC wave shape or DC curve, you would be able to calculate the amount of flux, and from that you can recalculate the equivalent AC values and determine the amount of flux, and with that method you can determine the saturation point. The instrument that Mike showed, MRCT instrument, has that IEC method available. We use the DC method to saturate the CT, and with that method you can test CTs as high as knee point up to 20 kilovolts. So for those special CTs which do not saturate with the traditional AC method of 2000 volt or less, we recommend using the DC method to saturate the CT and calculate or determine the knee point.
All right. Well, it looks like that's all the time we have for questions. We apologize if we didn't get to your question today, but we will follow up with you offline the next couple of weeks. Thank you all for attending. If you could, please remember to answer the survey. The survey will also include a field for you to request a quote or a demo if you're interested. Thank you all again for attending, and have a great week.